Thank you.
So in this series of 4 hours, we'll describe various basic techniques in the construction of pseudo-random objects and give some simple examples on how one can combine certain simple constructions to create a composed construction with considerably stronger properties. So we'll begin by giving some of the motivations and the main open problems in the complexity theoretic approach to pseudo-randomness. This will also lead to some of the issues that will be lectured on by David on extractors and expanders, and by Raghu on pseudo-random generator constructions. Perhaps one of the most important messages from this series of lectures will be that most of what we do in the complexity theoretic approach to pseudo-randomness is to use composition to take fairly simple objects and create those some with more elaborate properties. Then write definitions to abstract away details of what we have constructed and just kind of keep the important properties, and then combine them again and get something more powerful and so on. So we get this stack that eventually will get to extremely elaborate, extremely powerful constructions that David and Raghu will talk about. But they start from very simple components. Actually, in some cases, it's just those constructions are just composition all the way down. For example, in the zigzag construction of expanders, you say that to construct an expander of a certain size, all you need is an expander of a smaller size, and then one of a smaller size, and then of a smaller size. Eventually, just say, I need a fixed size expander that I can define as part of the definition of the construction. So there is nothing except composition. In other cases, the starting point for this stack of constructions would be very simple facts from algebra. And in fact, I think all of my lectures and Raghu's and David's, this will be all the algebra that we will use. The fact that if you have two linearly independent equations in n variables, the space of solutions will have dimension n minus 2. If you have a univariate polynomial that is non-zero as degree d can be 0 at most d times. So we will see how much mileage we can get out of those two things. So what I isolated maybe 3 types of problems that we're interested in solving in complexity theoretic pseudo-randomness. Although we will also see that they are just different facets of the same problems. Many of those questions have various alternative formulations, and things eventually they all are somewhat equivalent. So one general goal is to make the probabilistic method constructive, to show that maybe case by case, or even for some broad class of applications, if you're able to prove the existence of objects with certain properties by showing that a random object has that property with high probability, then we will also be able to use that as a starting point to come up with a completely deterministic and efficient construction of an object of this size. So here, efficient is a keyword because one can always make the probabilistic method constructive by enumerating all the sample space that you use in the probabilistic method proof, which will typically be exponential size. Maybe you show a random graph with certain properties. There are 2 to the n squared graphs with n vertices. You could just list all of them. But we will be interested in constructions where a graph is defined by a formula or maybe by a polynomial time algorithm. And the other goal, and we will see in which sense they are very related, is that if we have a probabilistic algorithm for a problem, which is efficient but has some small error probability, we would like to convert it, again, either case by case or through some kind of universal approach, to an algorithm for the same problem, which is deterministic, so there's no error and no use of randomness, but has comparable complexity. And again, comparable complexity is a key to this problem because you can always simulate a randomized algorithm deterministically by enumerating all the finitely many but exponentially many possibilities for its random choices. And then one more related question will be to construct objects that are fixed, or maybe they are distributions but with very small entropy, which have many of the useful properties, where here useful will depend on the application of truly random objects. So here again, efficient is an important part of the problem, but not even the only one, in the sense that it's not clear a priori that it is possible that there do exist deterministic or low entropy objects with many of the useful properties of completely random objects. And the fact that they do exist will be sort of part of what makes our theory interesting. Let me give you, so I said the three goals are make the probabilistic method constructive, make randomized algorithms deterministic, and create deterministic objects with useful properties of random objects. So to give some examples of how things we can prove with the probabilistic method, we would like to prove them constructively. Maybe we can start from the problem that gave birth to the probabilistic method, that of the Ramsey theorem in graph. So Ramsey, and then in this form, Erdős and Szekeres, proved that every vertex either has a reasonably large clique or a reasonably large independent set. Reasonably large in their proof was at least half times log n. So arbitrarily large graphs will have arbitrarily large cliques, arbitrarily large independent sets. So then it's a natural question, once you see the proof, that seems kind of very wasteful if log n is the right bound. And then Erdős invented the probabilistic method to show the log n was tight by showing that with good probability, if you pick an n-vertex graph at random, both the maximum clique and the maximum independent set will be of size about order of log n, 2 log n in this case. It's a factor of 4 between the upper bound and the lower bound. So this happened about 70, maybe almost 80 years ago. And ever since, there's been a really interesting question of whether we can construct graphs with this kind of property explicitly, as opposed to just saying that they exist, or that a random graph has this property with high probability. So there's been slow progress on this problem, with some breakthrough in the 80s, some breakthrough in the early 2000s, and another breakthrough last year. And now we are at the point where we can construct graphs. So here the goal is to get graphs where every clique and every independent set is as small as possible. So you want an upper bound as small as possible. Now we got to something that is exponential in polynomial in log n. So if this exponent was 1, exponential in log n would be log n, which is the right bound. Currently, this exponent is a bit bigger than 1, but it was a huge improvement from the last thing we had 10 years ago, which itself was a huge improvement over stuff from the 80s. And probably David will at least hint at how constructions like this work. So let me show another example that is like almost contemporary and another independent invention of the probabilistic method. So Shannon was interested in this problem, which I will not define completely because it has lots of possible choices, but the general flavor doesn't depend on those choices. So say we have two parties that can communicate to a channel that introduces errors, so it introduces noise. It's a digital channel, and the parties have digital information they want to send. Let's say this party A has a n-bit message they wants to send to B. So the way Shannon approached this problem was to say, well, let's see what happens if we... So then, in general, what party A will want to do is to encode X with some code, send the encoded message over the channel. The code will have some redundancy. And then the hope will be that the redundancies are such that even if noise happens, what party B receives uniquely determines what the message was. So Shannon says, well, what happens if we pick this encoding at random? and then the receiving party just decodes what it receives as the most likely message given the encoding and what it receives. So Shannon was able to prove that either this works with high probability, or I hope the information theorists that see this will not be too upset at this sloppy formulation. But roughly what he proved was that this method, in which the encoding is chosen randomly and known to both parties, and then the decoding is whatever seems most likely given those choices. So either this works with high probability, or there is no encoding at all, that with sending m bits over the channel, we'll be able to safely communicate n bits. So if anything works in this setup, a random code will work. Now, this was a very important existential result to say for every channel we can define a capacity, which is how much information we can transmit on the channel, which is achieved by a random encoding. But a random encoding is an object of double exponential size over the size of the message that you want to send, because it's a function over messages, so it's 2 to the n size. And decoding, if you don't have any specialized algorithm for it, which probably you don't if the code is random, will take exponential time. So the information theory community has endeavored very hard in the last 60, now almost 70 years in making those results constructive. And at least for some range of, at least for some choices of how you exactly formalize the problem, and for some range of the noise of the channel, we have optimal solutions where the decoding is polynomial or even linear or close to linear. And let's say something later about techniques that are not as good but provide non-trivial solutions to this problem. Let me give one more example. This is also by Shannon. It's a little different in flavor, but we will see how all those things are connected. So Shannon also considered, once he had this notion of information defined, he wanted to ask the following question. So suppose we have two communicating parties over A and B, over an insecure channel that is monitored by an eavesdropper. And let's say party A has some message X and also some secret key. B also knows the secret key that was agreed in advance. And now A would like to communicate X to B without the eavesdropper getting any information about it. So since Shannon had a definition of information, it would actually define rigorously this problem of doing communication with no information for the eavesdropper. And so his Shannon's solution was to say that party A should just send over the bitwise XOR of the message and the key. And then party B, so let's call this C for ciphertext. Then party B receives C, knows K, and it's able to reconstruct X as C XOR K. This XOR means bit by bit XOR. And now the reason why this is secure is that when the key is chosen randomly and not known to this adversary, the ciphertext is statistically independent of the message. It's just a random string with no mutual information with the message. So the eavesdropper has no idea about the communication. So in which sense this is okay? So what's so that's the good part about this code. It's somewhat usable. For example, diplomats could carry all times huge books of just random digits in their diplomatic pouch, and then whenever, or in submarines, they could have stacks of booklets with random digits. And then they could use unsecure channels to communicate securely. But so the reason why it's called one-time PUD is that if later there is some other message that party A wants to send to party B, cannot do the same thing again. Because then a lot of information about the message will leak. Because if later party A is also going to send C prime equal to Y XOR K, then the adversary, one thing they can do is to XOR C and C prime, and we'll learn the XOR of X and Y. That's a lot of information about the messages. That's why it's called the one-time party. So it would be much better if there was a way to use a key that much. Okay. So this system allows sending more than one message, but you need to use distinct parts of the key. So if you have a million-digit key, you can send 1,000-bit messages. But the constraint is that you cannot send messages that are longer than the key. But there is something that lots of people have been using for the longest time as a concept, which was that party A has some long message, which you can think of as being the concatenation of maybe lots of short messages that party A wants to send over time. And there is a short key, much shorter. And party B just knows the short key. And you have the same setup. So an approach that was generally used was for A and B to agree on some pseudo-random generator. Should be some procedure that stretches short keys into longer ones. And at the time, until the 80s, it wasn't clear how you would define such a thing. I mean, you would do it, but what property this had, it wasn't so clear. And then A would send over the message XORed with this stretched key to B. So in general, in what is called the stream cipher, G not only is able to stretch the key a lot, but you can compute the various bits online. You don't have to compute it all at once. So whenever you have a new message, you compute a few more bits of this huge output, and you use that with the one-time party. So then, I mean, this was done, but it wouldn't fit into Shannon's setup, because there is certainly mutual information between the message and the ciphertext. But you would still like to say something like, at least as a definition, that a generator is good if it's not possible to efficiently extract information from this ciphertext. And if you think about what would be a definition of a generator that makes such a system secure, you will come up with the same definition of pseudo-random generator that we will get at as a way of solving the problems that we talked about, like making the probabilistic method constructive, making randomized algorithms deterministic. So that's one more kind of classical problem from the 40s and 50s that can fit into the framework that we will talk about. So let me give you some examples of randomized. The three goals we talked about were making the probabilistic method constructive, so making things that use randomness more efficient, turn randomized algorithms into deterministic ones, and then create pseudo-randomness, whatever that means. So let me give some examples of randomized algorithms, some of them which we have been able, we as a community, to make deterministic, some of them we still have not been able to. One example is probability testing, given a large integer to check if it's prime or not, in time polynomial in the number of digits of the integer. So the idea that came in the early 70s of randomized algorithms for this problem was that when a number is composite, there are various certificates of the fact that it's composite. its factors are a certificate that it's composite. But there are other much easier to find certificates, such as equations that cannot possibly be true if the number is prime, because they would violate Fermat's little theorem or the quadratic reciprocity. And then what was proved in the 70s was that, in fact, for every composite, you can find, with high probability, a certificate that it's composite in time polynomial number of digits of the number. So that one approach to getting a non-randomized algorithm, one approach to get a deterministic algorithm for this problem would be to find a way to construct certificates of compositeness deterministically. So you see now, conceptually, it's not so different from saying we want to make the probabilistic method constructive. Somewhat similarly, we have something that we know exists with high probability, but we want to construct it deterministically. So actually, we still don't know, though maybe it's not such an important problem anymore, how to find Soloway-Strassen or Miller-Rabin certificates of compositeness for composite numbers. But what the AKS algorithm did, what AKS did to come up with their algorithm, was they first came up with a new randomized algorithm for this problem, which introduced a new class of certificates of compositeness. And then they found a way to construct those certificates deterministically. So in the new algorithm, if a number is composite, a certain polynomial in multivariate polynomial associated with the number is non-zero. If n is prime, that polynomial is always 0. So a certificate of compositeness is an evaluation point for the polynomial where it's non-zero. And then this we can find using randomness, because when a polynomial is non-zero, it's also going to be non-zero with high probability on a sufficiently large search space. But then they were able to de-randomize this and show that when this particular type of polynomial is non-zero, there is a small set of test inputs such that it will be non-zero on that small set. So the algorithm just checks the polynomial over that small set. So that's sort of the gold standard of de-randomization, of getting the randomized algorithm or making some variant of it, and then finding a way to construct whatever the algorithm is constructing, but without using randomness. So here's another famous algorithm, and it's derandomization. That's a graph algorithm. Given a graph where the edges are not directed, given two vertices, we want to see if there is a path from one vertex to the other. That's a problem that we can solve with linear time and linear memory. But an interesting observation from the 70s was that we can also solve it in polynomial time with constant memory, or log n memory, depending how you measure it exactly. And the algorithm is as follows. You start from one vertex. You do a random walk for up to order of n cubed steps. If you encounter the other vertex at some point in the walk, you know there is a path between them. If you don't encounter, you'll say there is no path between them. And then there is a simple analysis that shows that if t is in the connected component of S, a random walk of this length has high probability of hitting t. So the only amount of memory that you need for this algorithm is a counter to count from 1 to n cube, and a pointer to the vertex that you are at in the random walk. So the number of bits that it takes to store this constant number of variables is order of log n, where n is the number of vertices. It was open for about 30 years if we could match this performance without using randomness. And Omer Reingold, about 10 years ago, proved that you can solve this problem in polynomial time and order of log n bits of memory. And his algorithm could be seen as constructing polynomially many walks in the graph, such that if S and T are in the same quantity component, one of those walks will get there. In contrast, the number of walks that are generated with non-zero probability in this algorithm are exponentially many in n. So here's a problem we have no idea how to solve. It was I think it was a candidate polymath problem at one point. So let's say we are given a large integer n. We want to find a prime between n and 2 times n. So here's a randomized algorithm for this problem. Just pick a few numbers at random in the interval n to 2n until you get a prime 1. By the prime number theorem, on average, that will take order of log n time until you found 1. So can we have a sub-exponential? So here, log n is the size of the input. So this is a polynomial time algorithm. Can we get a sub-exponential in log n algorithm for this problem? That's a big open problem. Interesting, there was recently a non-trivial result about this problem, but it goes in the complementary direction of what we are talking about here. So we are interested in pseudo-randomness, which means things that are not random, ideally they are deterministic, but have some of the same behavior of probabilistic algorithms. Like here we know how to do this probabilistically, we would like to do it deterministically. So Shafii-Goldwasser has introduced the complementary notion of pseudo-deterministic algorithms. So those are randomized algorithms that have some of the interesting properties of deterministic ones. So what's an interesting property of deterministic algorithms is that if you give it twice the same input, you'll get twice the same output. This is not true for this method, because if you run it twice on n, you almost surely get 2 different primes. So her question was, is there a randomized, doesn't matter, algorithm for this problem that given n will find a prime, but almost always the same one. That depends only on n. And I think now there is a sub-exponential algorithm that does that. It's randomized, but it's pseudo-deterministic. So we will not return to this notion again because it's kind of completely complementary to what we want to talk about. It's the first almost non-trivial thing that we know about this problem. Here is a really important problem in our area. So suppose that we are given 2 multivariate polynomials. Given meaning that we have some formula for each of the 2 polynomials, or maybe we have an arithmetic circuit. Arithmetic circuit is like a little program with intermediate variables that says things like, you have variables x1, x2 up to xn, but you can also have intermediate variables y, z, and so on. So you can write things like y is equal to x1 plus x2, z is equal to y1 times x4. So given 2 polynomials in this form, multivariate, are they the same? The same meaning that if you were to express them as a sum of monomials, you get the same monomials with the same coefficients. So that's a problem that's an exponential time algorithm, which is expand the formula, look at the monomials, see if they match. It also has a polynomial time randomized algorithm, which is to just check the identity on a random input from a sufficiently big discrete space of inputs. It's a simple analysis that if you have more than the degree many choices for each variable with high probability, if those 2 polynomials are different, they will be different on a random input. Notice the AKS algorithm is based on, so an equivalent problem is given 1 polynomial, is it always 0? It's equivalent because you can look at P minus Q. So AKS, the primarily testing algorithm, solves this problem for a special type of polynomials, the one that come up in their algorithm. But it's open how to get a good algorithm for general polynomials, except if the formula is simple in some way, like a bounded depth. Here's another problem of a somewhat different nature. It has 2 equivalent formulations. Maybe you can read the first one. It's to, given a 0-1 matrix, it's to compute the permanent. The permanent is like the determinant, but there are no signs, just some overall permutations, these permuted diagonals. It's equivalent to say, given a bipartite undirected graph, compute the number of perfect matchings. So exact computations of this matrix parameter or graph parameter are unlikely to be possible. But there is a randomized algorithm that in polynomial time achieves arbitrarily good approximation. This is a result of Jerome, Sinclair, and Vigoda. And there is no known sub-exponential time, even sub-exponential factor approximation for this problem. This algorithm, the randomized one in polynomial time, achieves 1 plus epsilon approximation. But there is nothing. There's something slightly non-trivial, but there is really no comparable thing deterministically. Okay, this is the last example. It's the most abstract, but also in some way it encompasses all the others. So given a Boolean circuit, it's something where you have input wires that carry Boolean outputs, output wires that carry, the wires carrying inputs, wires carrying outputs, and then those wires are connected by gates that compute simple Boolean operations like AND, or not. And they can express computations of arbitrary algorithms through an appropriate encoding. So suppose I give you a Boolean circuit with a 1-bit output. You could consider essentially equivalently, I give you a small program that gives a 1-bit output. And I would like to approximate, maybe with an additive constant error, what is the fraction of inputs that make the circuit output 1? What's the fraction of inputs that make the circuit output 0? So there is a very simple randomized algorithm for this problem. Just look at what happens with a small sample. With high probability, you will get the correct fraction up to an error that is like 1 over the square root of the number of samples. So about deterministic algorithms for this problem. Well, maybe the problem doesn't seem so natural by itself, but if you had a deterministic algorithm for this problem, you could get deterministic algorithms for arbitrary polynomial time randomized algorithms. So this problem is sort of the hardest, or it completely encompasses all the problems encountered so far. That's just because whenever you have some algorithm that is randomized, you could encode what the algorithm does given the randomness as a circuit. And then if you're able to do that, you know whether your algorithm accepts with high probability or accepts with low probability. So that's a review of the type of derandomization problems that we would like to solve. There are some sort of open problems in complexity theory that relate to those questions. So the P versus PPP problem, which is essentially whether what I just described before is solvable deterministically, is the question of whether we can transform every polynomial time randomized algorithm into a deterministic one. And there is some evidence that this might be possible, in the sense that there are standard conjectures in complexity theory that imply that this conjecture is true, that every randomized algorithm can be converted to a deterministic polynomial time one. Unfortunately, it also implies certain circuit complexity conjectures, which seem very hard. So it's unlikely that we will see progress on this problem in the, somehow.
It would be very good if we could see progress on this problem.
Yes.
In this program.
Yes, I think that's better said. Hopefully we will see progress on this problem. So the point really I want to make is that although this is an algorithmic problem, it's essentially also a circuit complexity problem. Circuit complexity has been the bane of complexity theory for the past 40 years. So, but maybe algorithmic thinking is what's needed to make progress there. And so here is a conjecture for which we don't have any barrier, meaning we don't know that it implies things that we are scared about proving, which is the same question as before, but not for just polynomial time algorithms, for algorithms run both in polynomial time and using order of log n bits of space, like the algorithm for finding paths in graphs. So that algorithm we know how to derandomize. We don't know if that's true for every algorithm that runs in polynomial time with order of log n space. And here we know a somewhat non-trivial result. By now it's probably 20 years old, 15. No.
Closer to 20. Yeah.
Closer to 20, yeah. So that we can, if a problem can be solved in polynomial time with log n bits of memory using randomness, it can also be solved deterministically with root log n extra memory and not polynomial, but a little bit more than polynomial time.
Whose result was that?
Saxon's Jew.
Yeah, Sachs and Joe. All right, so let me introduce one notion that will be fundamental to what I will talk about and also what Raghu will talk about, which is sort of what underlies all those questions and many of those results. So maybe before, and also it's the solution to that question of how we get one-time path to be secure if the key is short. So the kind of notion that we have in mind is that we would like to have some procedure, a deterministic one, that takes a small amount of randomness, maybe even no randomness at all, and that's usually not possible, and then it stretches it to a much bigger output in such a way that this output has many of the useful properties of a truly random output, even though it has such a small entropy. So how do we say rigorously that it has many of the interesting properties of a truly random function, a truly random string? So we start by thinking about our problem domain and identifying some statistical properties that we find important. Statistical properties just means Boolean functions of those strings. So they don't need to be Boolean, but let's say they're Boolean. So then we say that a generator is good with parameter epsilon for this family of statistical tests if for every statistical test in the family, the probability that it's true for a truly random string is the same as the probability that it's true for the output of the generator, plus or minus epsilon. So so those constructions are good. The more general is the family of statistical tests for which we can get them. But in general, it's good if it works for the family of statistical tests that make sense in our applications. And it's also good when this parameter epsilon is small. Although usually once you get epsilon to be something like 1%, there is some way of getting arbitrarily small one. Okay, so that's the definition that we will work with. A very important case will be where the collection of statistical tests that we are interested in are all tests computable within some time bound, all efficiently computable tests. Because that will mean that the output of the generator has all the checkable properties of truly random strings.
Sorry, so just to, you didn't write what actually it is, so it's the probability that
yeah,
f of g of x is different from f of x?
Yeah, let me, I think I left it blank to add it now. So the requirement is that for every function in the family, the probability that f is 1 when given an x sample from the uniform distribution over n bits is the same as the probability that f is 1 when evaluated on a random output of the generator. plus or minus epsilon. Yeah, so that's the definition of the generator, that the generator epsilon fools the class of tests calligraphic F. And then for various instantiation of what tests we are interested in, we'll get different types of generator. Some of them we know how to construct them with really good parameters. Some of them we know to construct them only under circuit complexity assumptions. So here would be the so something that would more or less solve all our problems in the area. If we could have some, so here there's always a parameter n, so you should think of this as not being just finite objects, but families of constructions. If we were able for every n to come up with a generator that stretches the input exponentially, so that goes from log n bits to n bits, and such that this exponentially longer output is still fooling all polynomial time, but say it's n squared time computable statistical tests. It's a bit tricky what you mean by an algorithm that runs some n squared on a fixed size. So in this case, it's good to take circuits as our definition of what is an algorithm, and size of the circuit as our definition of what is running time. But someone should translate in your mind always circuit to algorithm and size to time. This is just what makes rigorous sense, but algorithms is what we want to capture.
So circuits of size n squared is the number of variables in there?
No, size means the number of gates or the number of wires, but let's say the number of gates. So those circuits take n inputs, so those circuits are meant to be evaluated on the output of the generator, so they have n inputs and one output. So if we were able to get generators with this kind of property, polynomial time computability, exponential stretch, and ability to fool all, say, fixed polynomial tests, then we would have a number of consequences. But first, let me ask for.
Is this slightly stronger than, say, being able to fool all programs of descriptive complexity log star n and runtime at most n squared or something?
Yeah, it's a little stronger. So that would only, I think, give you a way to de-randomize good on average algorithms, not good on worst case algorithms. Because if I can come back to that, when I show why this implies P equals BPP, we can see why what you asked does not give P equals BPP. It's a very good question. So I want to argue that if we had generators with those kind of properties, we would have almost all that we want in the area. So all probabilistic algorithms can be de-randomized in polynomial time. Most applications of the probabilistic method can be made constructive. Not all of them, just those where the property that you're looking for has a polynomial time algorithm to check it. So even if we had this kind of great generators, we still would not know how to get the best possible Ramsey graphs, because the property of being a Ramsey graph, we don't know how to check it in polynomial time. But also, all randomized approximation algorithms, we can get deterministic approximation algorithms. For algorithms of every type that are good, if we have randomness, we can simulate them without randomness. So let me prove for you how you get those consequences, because in a way, those proofs will motivate the definition, so that you will see why the definition is exactly what makes those proofs work. Yeah, it's a little.
For the Ramsey graphs, it was still running quasi-poly time, right?
Yeah. So, but in that case, with no assumptions, you can get n to the log n time constructions of optimal Ramsey graphs, because there, and actually, we will build enough tools to do that by the end of the next lecture. But yeah, that's a good point. Yeah, so Ramsey graphs, it's a little easier than other problems, because it's true the search space is sized. Yeah, so for many problems, we don't know how to get any sub-exponential time construction. But for Ramsey graphs, we will see we can get n to the log n time constructions. All right, so let me show you these implications. And I think they will really clarify what the definition is doing. So suppose we have some problem that we know how to solve with a polynomial time randomized algorithm. So maybe we have some algorithm A. I write it as a box. So algorithm A takes an input x, takes some randomness, runs in polynomial time, say if the input x has length n, A runs in n cube time, and so the randomness is also of length at most n cube. So then it has an output. Let's say this is a problem with a 0-1 type of output, and it's correct with 90% probability. So here is what. So first of all, how do we do this in exponential time without knowing anything? We give an x. We just try all possible choices for r, of which there are 2 to the n cube. We see when the algorithm outputs 0, when it outputs 1. We list all these answers. Either we see at least 90% zeros, or we see at least 90% ones. And whichever it is, the majority answer is the correct answer. So that's how you would do that in exponential time. But now suppose you had that great, excellent type of pseudo-random generator that I postulated before. Now the first step is to see that if I run the algorithm on so if I now run the algorithm using as source of randomness not an actual sequence of random bits, but the output of the generator, I want to claim the algorithm is still 80% probability correct. Why? Because so let's consider those two probabilistic experiments. We run the algorithm on valid randomness. We run the algorithm on the output of the generator. So here, the correct answer, whichever it is, comes out 90% of the time. Suppose here, it came out less than 80% of the time. Then the probability that the output of the algorithm is, say, 1 here, will differ from the probability that the output of the algorithm is 1 here by more than 10%. So suppose here it's correct with less than 80% probability. Suppose here we know by our analysis it's correct with more than 90%. So then it must follow that the probability the algorithm outputs 1 here differs from the probability the algorithm outputs 1 here by more than 1/10. So now let's regard the algorithm together with its input as being our f. And also now our n is whatever is the original. So now we're looking at comparing what a certain function does given the output of the generator compared to what it does given a truly random input. Now, the length of this input, just call it big N, it will be whatever is the polynomial running time of the algorithm. Well, here, what is this f? It's what the algorithm does on input x given its randomness. And it's something that is doable in time little n cubed, so order of big N, which is much smaller than n squared. So what we have here is an f that is computable in size much less than n squared, and it's not 1/10 fooled. So being fooled by generator means that the output distribution with true randomness is the same as the output distribution with pseudo-randomness up to the parameter, which is in this case is 1/10. So if here you're usually correct and here not, it means that you're not fooling f. F is some statistical property that distinguishes those two cases, and it is efficiently computable, and so it contradicts the security of the generator. And if the generator has the security properties that we talked about, such a scenario is not possible, which means that here we are correct with pretty more than 80%. Now, coming back to Daniel's question, our class of statistical tests will have to be whatever shows up in this proof. So, which in general will be algorithms together with an input and how they operate on the randomness. So those are efficient algorithms, but they have pretty big descriptions, because part of the description of the algorithm is also what input it gets. So that's why we use circuits to model adversaries, which somehow allow algorithms of arbitrarily big description without being too technical about it. Okay, so the proof is not finished. Since we reached a contradiction, what we had here is not possible. So here we're also correct with probability more than 80%. But now all the randomness in this process are these order of log n bits that we input here. So what we can do is to run this system over all possible choices of these order of log n random bits. Now the number of ways you can choose order of log n bits is 2 to the order of log n, so it's polynomial in n. G is computable in time polynomial in n. A is a polynomial time algorithm. So the whole thing can be done in polynomial time. And then what you will get is the set of all possible outcomes of this process over all possible randomnesses. So either you will see 1 appearing 80% of the times or more, or you will see 0 appearing 80% of the times or more. And whichever it is, that's the correct answer for the problem. And now there is no randomness left in the process. It's a deterministic polynomial time algorithm for the original problem. And so if you start from the proof and then you work back what definition makes this proof work, that's the definition we gave. There is no other choice. Any questions about this? Yes?
So are there candidate like log n to n generators? Like, could I start using, de-randomized algorithms today if I believe in them?
Yes. Unfortunately, the problem is also the constant in that log n. I think.
So are there some kind of Cook's, diagonalize kind of or dovetail over all machines thing, or no?
No. So you have to rely on unproved assumptions.
Okay.
So you there is a general theory that says that if there is some problem that you can solve in exponential time, but not by circuits that are of size less than exponential, a construction like this works. There is some encoding happening in the construction. So either for n equal maybe 1 million, the seed length might be several hundreds, and you really cannot do 2 to the several hundreds. So for this to be doable, the seed needs to be no more than 30 or 40 bits. And none of the approaches that we have can be so conservative that really gives a generator with 30 or 40 bit seeds. You could take cryptographic constructions that are believed to have really tight hardness and re-instantiate them so they really have seed length of 30 or 40 bits. And actually, it might be interesting to see what happens if you do something like that.
Just as a clarification, so such a G exists, not computable, but just as if you took G at random, just counting overall A, you can use turn-off bounds.
Yeah, that's another good point. So if you don't care about G being polynomial time computable, if you pick G at random among all functions and map order of n bits to n bits, it will have this property almost surely. So the reason why what makes the question difficult is that we want a polynomial time computable G, which if it exists implies circuit complexity consequences that are kind of beyond reach of current techniques.
So in your definition of this problem, are you distinguishing between statistical properties where there are many of them, but that's because you have some auxiliary input, and just a very, very large collection of statistical properties which may be very hard to describe efficiently? So are you accepting if I have sort of a trillion statistical tests and it takes me exponential time to write them all down, and that defeats your scheme, is that still allowed?
Well, we want to distinguish from the definition to the domains in which it's applicable or useful. So the definition is well given for any family of tests, so regardless of their complexity or their cardinality, their description, and so on. Usually, the interesting applications of this notion are in contexts where those tests are certain types of algorithms. And then they will have both efficient evaluation and a reasonably small description. I'd also like to, in this last minute, actually maybe I'll leave it on this proof and then we'll return after the break. So what I want to show later is a different language in which to give the same definition that looks a lot more like the language in which you say things like the smoothed indicator function of the primes is pseudo-random or Mobius function is pseudo-random. And then see how from this you get a constructive version of the probabilistic method. And then we'll start constructing generators with non-trivial pseudo-randomness properties. Not these pseudo-randomness properties, but some pseudo-randomness properties. So, thank you.